Assalamu alaikum, my dear cadets. I welcome you all. It's a very critical moment to you where the novel coronavirus has scattered everywhere in our country and also all over the world. So be safe and sound and stay your home. Don't go anywhere. However excellent you are, I am Mohammad Ashikur Rahman, lecturer in chemistry at Borishal Cadet College. Today I am going to start my lesson on chapter 2. The title of the chapter is Organic Chemistry, which is included to your chemistry second paper. And the topic which you will be taught today is the concept of carbocation and carbanion. By the end of this lesson, cadets, you will be able to classify carbocation and carbanion, explain the stability of carbocation and carbanion, and finally you will be able to discuss the properties of carbocation and carbanion. Now move on to the structure of and stability of carbocation. First of all, we have to solve a question, that is, what is carbocation intermediate? A carbocation is an organic molecule, an intermediate that has a carbon atom bearing a positive charge and 3 bonds instead of 4. That means carbocation comes from two words, carbo and cation. Carbo means carbon atom and cation means a positive charge. That means carbocation is a chemical species which contain a carbon atom with positive charge. For explanation, since the charge carbon atom does not satisfy the octet rule, it is unstable and therefore highly reactive. Now the classification of carbocation. Carbocation can be classified into 3 types, that is primary, secondary and tertiary carbocation. A primary carbocation is also known as 1 degree carbocation. 1 degree carbocation contains one alkyl group, that means 1 R and 2 hydrogen atom. A secondary carbocation is also known as 2 degree carbocation, which contain 2 alkyl group, that means 2 R and 1 hydrogen atom. And a tertiary, that means a third degree or 3 degree carbocation contains 3 alkyl group, that means 3R and no hydrogen atom in this case. First of all, so we can say that a primary carbocation has one carbon group, that means one alkyl group attached to the carbon bearing the positive charge. A secondary carbocation has two carbon, that means two alkyl groups attached to the carbon bearing the positive charge, and a tertiary carbocation contains 3 alkyl radicals with positive charge and a carbon atom. Now the structure of different carbocation. Consider, here we see a carbon atom and here 3 alkyl radical are bonded with the carbon atom, and here you also see that a positive charge is on the carbon atom. So this carbocation is called tertiary carbocation because here three alkyl group present here. This is one alkyl group, this is another, and the third alkyl group is here. So the total number of carbocation is are 3 here, which is bonded to the positive carbon, so it is called 3 degree or tertiary carbocation. Next, here only two alkyl group is bonded to the positive carbon atom. It is one alkyl radical and it is another alkyl radical, so the total number of alkyl radical is 2 here, so it is 2 degree or secondary carbocation. And here and next we see that only one alkyl radical is present here, which is bonded to the positive carbon atom. This is the alkyl radical, so it is called 1 degree or primary carbocation. And finally we will see that this carbon atom contain no alkyl radical. Here the carbon atoms is bonded with only 3 hydrogen atom, and here we see that no alkyl radical is present here, so it is known as 0 degree or parent carbocation. This is simply it is called methyl carbocation. And we can say that the 3 degree carbocation is more stable than 2 degree carbocation, and the 2 degree carbocation is more stable than 1 degree carbocation. Similarly, 1 degree carbocation is more stable than 0 degree carbocation. But how the stability we can be understand? It is clearly understand by the following. Now we will consider the stability of carbocation. First of all, consider the carbon atom. Here 3 hydrogen atom is bonded with the positive carbon atom, so this is called 0 degree carbocation because it contains no alkyl radical. Here we see that the carbon atom contains a positive charge, and also it contains 3 single bond, and we know everyone that each bond contain 2 electrons, so the total number of electrons around carbon in its outermost shell is 6. So the 0 degree alkyl carbocation is obviously are in incomplete octet state. In the next one we will see the carbon atom attached with 2 hydrogen atom, and also an alkyl radical is present here, and in this case it is called 1 degree carbocation, as an alkyl group is present here, and we know each alkyl group acts as an electron releasing group. So these alkyl radicals donates electron to the positive carbon atom, so the positive charge can be easily neutralized by the alkyl radical in this case. So in case of 1 degree carbocation, this positive charge will be neutralized, so nearly gain an octet field condition in this case as compared to 0 degree carbocation. So 0 degree carbocation is less stable than 1 degree carbocation, because in case of 0 degree carbocation it is in incomplete octet state as compared with when it is compared with 1 degree carbocation. Now consider, so we will say that 0 degree carbocation is less stable than 1 degree carbocation. Now we will follow the next example, that means consider the carbon atom where we see that one alkyl radical is bonded with a positive carbon, so it is called 1 degree carbocation. And then consider the next atom, which is carbon atom contains 2 alkyl radical, so it is called 2 degree or secondary carbocation. Here in case of 2 degree carbocation, the 2 alkyl radical donates electron to the positive carbon atom more and more as compared to 1 degree carbocation, because in case of 1 degree carbocation only one alkyl radical is present here, so the donation of electron is not more as compared to 2 degree carbocation, because it contains 2 alkyl group radicals. So these alkyl radicals donates more and more electron to the positive carbon atom in 2 degree carbocation. So in case of 2 degree carbocation, the positive carbon atom can be easily neutralized by the 2 alkyl radicals. So we can say that 1 degree carbocation is less stable than 2 degree carbocation. That means 2 degree carbocation is more stable than 1 degree carbocation. Now consider the next example. Here carbon atom is bonded with 2 alkyl group and also 1 hydrogen atom. So as this carbocation contains 2 alkyl radicals, it is one and it is another one, so it is called 2 degree carbocation. And the next one, here 3 alkyl radical is bonded with the positive carbon atom, so this is called 3 degree carbocation. Similarly, we can say that in case of 3 degree carbocation, the 3 alkyl groups donates electron more and more to the positive carbon atoms, so this positive carbon atom can easily be neutralized by the 3 alkyl by these 3 alkyl groups. So in case of 3 degree carbocation, it is easily occupied the octet field condition when it is compared with 2 degree carbocation, because in case of 2 degree carbocation only 2 alkyl group is present here, so this alkyl group donates less electron to the positive carbon atom as compared with 3 degree carbocation, because 3 degree carbocation contains 3 more alkyl group than 2 degree carbocation. So 3 degree carbocation is more stable than 2 degree carbocation. Reversely, we can say that 2 degree carbocation is less stable than 3 degree carbocation. So what determines carbocation stability? The delocalization of charge stabilizes the carbocation. Thus, the more alkyl groups there are surrounding the cationic carbon, the more stable it becomes. So the order of stability of carbocation will be the following order. 3 degree is more stable than 2 degree, and similarly 1 degree and 0 degree. That means 0 degree carbocation will be the less stable carbocation in this case here. So cadets, think about the following example. Which one is more stable? In case of 3 degree, consider the cadets, you will follow this example. Here we see that only 1 alkyl radical is present here, so this is 1 degree alkyl carbocation. Consider the another next one example. Here we see that here this carbocation contains 2 alkyl radical, so it is known as 2 degree carbocation or secondary carbocation. And the last one, this configuration contains 3 alkyl radical, so this carbocation is known as tertiary or 3 degree carbocation. Now we will discuss what determines carbocation stability. There are 3 factors to determine the stability of carbocation. First of all, the multiple bonds. Second one is lone pairs electron, and the third is alkyl radical. First of all, we will discuss the adjacent multiple bond. An adjacent pi bond allows the positive charge to be delocalized by resonance. Resonance, do you know what is the definition of resonance? It's simply that the delocalization of electrons is known as resonance, which will be discussed later. In this way, we can say that the first carbocation, which is left side, is more stable than the right side carbocation. The reason will be discussed later. First of all, we will discuss the factors adjacent multiple bonds. If a compound contains a pi electrons which is adjacent to the positive charge, then this carbocation will be more stable than others which contains no adjacent multiple bonds, that means adjacent double or triple bond. For example, CH2 double bond CH2 plus is more stable than CH3 CH2 plus carbocation, because in this case of first carbocation resonance is possible, which is shown here. Here you see that this is the pi bond which is shifted to the positive charge, and so this positive charge is neutralized easily and create a new pi bond in here, and after movement of this pi electron a positive charge is created here, and in this way two configuration is possible. And you see that here the positive charge shifted from one carbon to another. This shipment, that means this movement, is called delocalization. Localization means when a positive charge is placed in the same state or same place, then it is called localized electron. And if any charge will move from one carbon to another carbon, then this state is called delocalized state, and the delocalization of the charge is called resonance. In this way, this ion contains resonance, because here the electronegativity of oxygen is more than the carbon element or carbon atom, so the pi electron will move towards the oxygen atom, and in this case, as a result, a negative charge is created here on the oxygen atom, and after movement the pi electrons to the oxygen atom, the carbon bears a positive charge, and here we will see that positive charge, the movement of positive charge has taken place in this case, so we can say that delocalization or resonance has been taken place. So this ion will be more stable than that of ion which contains no pi bonds. The second one, adjacent lone pairs of electron. A lone pair on an adjacent atom stabilizes a carbocation. Here consider the following example, which is CH3O CH2 plus. And another example is CH3 CH2 CH2 plus. Here we see that in case of first carbocation or first ion, it contains a hetero element which is oxygen and which contains a lone pair electrons, and that another example, another ion contains no hetero element and which contain no lone pair of electrons. So in the first example we will say that in this case the oxygen atom in from here the lone pair electrons shifts to the positive charge, and the positive charge on carbon atom can be easily get neutralized here, and as a result a positive charge is appears on the oxygen atom. So there are two state is created here. So we can say that positive charge movement is possible is taken place here. So the delocalization or resonance has been taken place here. So this ion is more stable than the others which contains no hetero element. That means where delocalization is not possible. Now consider the third factor, which is adjacent carbon atoms. That means adjacent alkyl radical, which was already discussed in the previous section. The stability of carbocations increases as we add more carbon atoms, that means more alkyl radical to the cationic carbon. As for example, CH3 CH2 plus is more stable than CH3 plus, because in case of ethyl radical, which is in case of ethyl radical, it contains one alkyl radical which is methyl radical, and in case of methyl carbocation there is no alkyl radical is present here. And we are already known that if alkyl radical increases, then the stability also increases. So in this case the ethyl radical is more stable than methyl radical. The stabilization is explained by a type of resonance called hyperconjugation, which will be discussed session. In this case we will follow that the sigma electron between the carbon hydrogen bond will is shifted to the carbon atom which contain a positive charge, and in this case and in this way the positive charge is easily neutralized by that electron, sigma electrons, and here a positive charge is created on the hydrogen atom. Simply you know that you will be remind that the shipment or complete transfer of sigma electron from another element to another element is known as hyperconjugation. These topics will be discussed later elaborately. The sp3 orbitals of the adjacent CH bonds overlap with the vacant p orbital on the carbocation. So we will discuss the next topics, which is carbocation. So boys, do you know what is carbocation? What is carbanion? A carbanion is a carbon atom which contains a negative charge, where a carbocation contains a positive charge. In this case of carbanion, a carbon atom contains a negative charge. So as the carbon atom contains a negative charge, so the carbanion is in octet field chemical species. Consider the first example where the carbon atom contains a negative charge, and here 3 hydrogen atoms are bonded to the negative carbon atom. Here we see that it contains 3 sigma bond and so the total number of electron is 6, and the negative charge included here, so the total number of electron will be 8. So this carbanion is in octet field state here. Now the classification of carbanion. Carbanion also can be classified into 3 types, which are primary, secondary and tertiary carbanion. In primary carbanion, it contains one alkyl group and 2 hydrogen atom. In secondary, that means 2 degree carbanion, it contains 2 alkyl group and 1 hydrogen atom, and in case of 3 degree or tertiary carbanion, it contains 3 alkyl group and contains no hydrogen atom. Now we can say that we can discuss the structure of carbanion. First of all, here we see that a carbon atom with a negative charge contain 3 alkyl group. So this is known as 3 degree carbanion because it contains 3 alkyl group but no hydrogen atom. And in case of, and the next one, here we see that the negative carbon atom contains 2 alkyl groups and 1 hydrogen atom, so it is called 2 degree or secondary carbanion. And the next one, here we see that the negative carbon atom contains 1 alkyl group and 2 hydrogen atoms, so it is known as 1 degree carbanion. And finally, this is the last one. Here we see that the carbon atom contains negative charge, contains 3 hydrogen atoms, so it is called 0 degree carbanion. The 3 degree carbanion is less stable than 2 degree carbanion, and the 2 degree carbanion is less stable than 1 degree carbanion. And finally, in similar way, the 1 degree carbanion is less stable than 1 degree carbanion, which will be discussed following. First of all, consider the carbon atom which contains a negative charge, and you will see that this carbanion contains 3 hydrogen atom and no alkyl radicals, so it is 0 degree carbanion. The next one, we see that the carbon atom with negative charge contains 1 alkyl group and 2 hydrogen atoms, so it is known as 1 degree carbanion. But boys, you see that in case of 0 degree carbanion, the carbon atom is in octet field state, so it is stable state, we can consider it. But in case of 1 degree carbanion, we see that here 1 alkyl group is present here, and we know that all alkyl group acts as an electron releasing or electron donating group. So in this case, the alkyl group donates electron to the negative carbon atom, so the electron density increases more and more. So the octet field carbanion contains more and more electron density as compared to 0 degree or methyl carbanion. So here 0 degree or parent carbanion is more stable than 1 degree carbanion, because in 1 degree carbanion contains more than more electrons than in octet field condition. So we can say that 0 degree carbanion is more stable than 1 degree carbanion. Consider the next example, where we will see that a carbon atom contains a negative charge, has 1 alkyl group and 2 hydrogen atoms, so it is known as 1 degree carbanion. And consider the next carbon atom which contain two alkyl group and one hydrogen atom. So it is called 2 degree or secondary carbanion. In case of when we compared between 1 degree and 2 degree carbanion, hence we can say that 1 degree carbanion is more stable than 2 degree carbanion, because the 1 degree carbanion contains one alkyl group and 2 degree carbanion contains two alkyl group, and hence the two alkyl groups donates more electron to the negative carbon atom, which is already are in octet condition. So when we compare between this carbocation, we will say that the 1 degree carbocation is more stable than 2 degree carbocation. In similar way, we can be explained that the 2 degree carbocation is more stable than the 3 degree carbocation, because in case of 2 degree carbocation it contains 2 alkyl group, and in case of 3 degree carbocation it contains 3 alkyl group here. So in case of 3 alkyl group, the 3 alkyl groups donates more and more electron than that of 2 degree carbanion. So so we can say that the 2 degree or secondary carbanion is more stable than the 3 degree carbanion. So what determines carbanion stability? The more alkyl groups there are surrounding the anionic carbon, the less stable it becomes. So the order of stability of carbanion will be 0 degree, 1 degree, 2 degree and 3 degree here. Now how do you differentiate between free radical, which has been discussed in the previous lesson, and carbocation and carbanion? The explanation as follows: free radicals are molecules that have an unpaired electron. This makes them very unstable and they rapidly combine with other species that are trying to gain a valence electron. In case of carbocation, which contain a carbon atom with a positive charge, and in case of carbanion, which contain a carbon atom with a negative charge. So after ending this lesson, some of the findings are here. First of all, the order of stability of for free radicals is here. The order of stability for carbocations is here, and the last one, the order of activity for carbanion is here. Now the home task for you cadets. First of all, you have to explain what stabilizes the carbocation, and then you have to explain what stabilizes the carbocation, like this figure, and next you have to explain what stabilizes the carbocation, the following figure. Next, explain what stabilizes the carbocation to the following figure, and finally a creative question which is shown here. The stem contains 3 alkyl group with a negative carbon atoms, which is 3 degree carbanion, and then it is 2 degree carbanion which contain 2 alkyl groups, and finally 1 degree carbanion which contain 1 alkyl group. So cadets, be safe and sound and stay at home during the COVID-19. Don't go anywhere from your home. So best of luck. Thank you, and thank you all.